or just?
Maybe just begin. You can. I can begin directly. Start directly.
Okay.
Okay, then I think it's the time.
Great. We'll start with our next speaker. Xiaojun will be talking about open Wi-Fi, and I'll hand it over. Thank you very much.
Thank you. Thank you, everybody. I know you are tired or sleepy. It's a long afternoon or long weekend. So my presentation will be in a different way. You don't need to ask question. I will ask question for you to myself. In this way, I try to attract you from beginning to the end. First question, very basic. What is open Wi-Fi? It's not the Wi-Fi that give you open access all over the world. I know there is such a project also called open Wi-Fi. Unfortunately, or fortunately, this is not. The answer is that open Wi-Fi in our project, it represents the open source IEEE 802.11 of Wi-Fi chip design. Before this project, I think many people only have one choice, use some commercial Wi-Fi chip. But after this project, you have one more choice, open source Wi-Fi chip. But in this phase, it's not a real Wi-Fi chip yet. It's running in the IPGA. As you must know that IPGA is, or IPGA verification is a very important step before you tape out a real Wi-Fi chip, right? You use IPGA to verify your IC design is correct. So current phase is IPGA design. You can just Google open Wi-Fi. You will find our GitHub repository. Currently, I think it's in top 3 or top 4 item in the Google search engine. Well, maybe it depends on your browser or how or your most frequent searching word in your browser. But in my browser, it's the third one. Okay, why we say it's a chip design or Wi-Fi chip? Because it's not like it works not like the USRP or GNU radio stuff. It's really work like a commercial Wi-Fi chip. You may know or you may not, the commercial Wi-Fi chip actually offer you two things. The first one, the silicon, right? The chip itself. The second thing is the driver. Most of time, I guess we use the Linux driver. Then that's it, right? You insert the dongle, the driver is auto-loaded, or you install it. That's how commercial Wi-Fi chip works. Our design also works exactly in the same way. We offer you the chip design, which is IPGA currently. We also offer you the open source Wi-Fi driver, which works below the Linux native Mac 802.11 Wi-Fi framework. This framework is used for almost all the commercial soft Mac architecture Wi-Fi chip. We also offer you a very tiny tool, user space tool to communicate with our driver and IPGA. So that's the basic architecture. As you can see, same as commercial chip. Actually, if you go to our demo, you can use your cell phone to connect our the chip, the Linux run over the chip, and there's host APD, there's a web server. You can access it, just like you access commercial Wi-Fi router. Nice. Okay, next question. I guess in your mind is that, is the open Wi-Fi chip better than commercial Wi-Fi chip? Right? That's the quite direct question. Why should I use your chip? Is your chip better? The answer is no. And I remind you, this is not a joke. Disappointed, right? Well, as you may know, those commercial Wi-Fi chip, they support quite new standard, right? AC, AX, and they support many antennas, right? Advanced MIMO processing, MIMO or high order MIMO. And they also support very high bandwidth. That means very high throughput, right? 20 megahertz, 40 megahertz until 160 megahertz, right? Those chips are quite advanced. Unfortunately, our chip in this phase is not as advanced as theirs. Currently, our chip works only in 11A, 11G, and 11N mode. In all the frequency below 6 gigahertz. That means you can set it into 2.4 gigahertz or 5 gigahertz. 11 AGN, and currently it only supports 20 megahertz, which means the highest throughput is around 50 or 60 megabps, right? The theoretical peak data rate of the physical layer. So it's a technology maybe many years ago the industry has achieved, right? We rebuilt the Wi-Fi chip again by ourselves. Well, I would say maybe so far we identify at least one point, maybe it's attractive or a little bit better than a commercial Wi-Fi chip. The point is that our design currently is based on the system on chip, the Xilinx Zinc FPGA, with the ARM processor embedded. In that case, our full Wi-Fi stack, including from the Linux application to the baseband, are in the same chip. As you can see, the red circle, those Linux operating system, user space, kernel, driver, and FPGA, not the front end. All these things in the same chip. So we have one, well, not so big advantage is that if you ping our node, right, because it's Linux, you can ping it. It has an IP address. Your echo speed, or the ping round trip latency is lower than the commercial chip. I think when you do the ping over commercial chip, your round trip ping latency is always, I guess, around 1 millisecond. In our design, you can have around 0.6 or 0.7 millisecond. Because it is the SoC, system on chip, right? So that's why we also need to offer you the Wi-Fi driver. You cannot use any other commercial Wi-Fi driver. Because the commercial Wi-Fi driver always works over the USB bus or PCIe bus, right? But in this chip, there's no, the interface between our Wi-Fi chip, which is FPGA, and SDR driver. Here, the interface is not USB or PCIe. It is the Xilinx on-chip bus, which is the AXI Stream or AXI memory mapped DMA controller. So that's why we have to develop the Linux driver for this quite special on-chip, low latency, high throughput link for our Wi-Fi design. Okay, if Open Wi-Fi is worth, why should I use Open Wi-Fi? Well, this is the key part. I try to answer the question to convince you. Okay. But this time, I remind you, this is a joke. So why you should use the Open Wi-Fi design? Well, very direct usage of this design is for education, right? It's quite obvious. If you are a researcher or a professor in a university, you try to teach your students how exactly a Wi-Fi chip runs. If you buy a commercial Wi-Fi chip that has the black box silicon, you don't know what is inside. How can you teach students know-how knowledge of Wi-Fi chip run? So with this design, you have the full stack, right? Open full stack from the user program in Linux to the antenna. I mean, in the IPGA, there's also logic to control the front end and antenna, as the antenna selection, TX, gain, RX, AGC stuff. Everything works just like those modules in a commercial chip. Okay, for the secondary usage, right, there could be many. You may have ideas to improve Wi-Fi chip or customize the Wi-Fi chip for your special application. If you run a business, maybe you have some special customer in the aviation industry or railway industry, right? They have very special requirements to your Wi-Fi communication system. And you may try the commercial Wi-Fi chip at first. Maybe it's perfect for your application. Then you forget Open Wi-Fi. If commercial chip is not good enough, you try to tailor or customize the commercial chip, right? You go to the big commercial company. The first question you get will be how many PCS you will buy from our company per year, right? If you say 1,000 chips, then I think you don't have any chance. You should try our design, tailored, customized for your special application. And if you are using some full MAC Wi-Fi chip, not the soft MAC, which means that the Wi-Fi chip is very complicated. All the MAC layer, link adaptation, everything, advanced control is in the chip. In that case, you don't have full control of the chip from the driver. Maybe if you want some special functionality, you need to reverse engineer a little bit the chip, firmware in the chip, right? That's the most of the Wi-Fi security researcher or Wi-Fi researcher currently do the reverse engineering of the firmware of the Wi-Fi chip. But with this design, you have the transparent design, the fully controlled functionality. And okay, you want to modify Wi-Fi chip, it's not possible. You want to see how your new component work with Wi-Fi, how your new component will improve performance of Wi-Fi network, such as you make a new PA, right? High power amplifier for long range. You make new LNA. You make new antenna or beam antenna. Make new algorithm. You can test your component, your idea, or your algorithm on over the Open Wi-Fi design. Actually, before the project was announced, last Christmas, we already had some seed user in the ORCA project, which is the Horizon 2020 European project. And they are using the Open Wi-Fi board in our testbed. They are doing some amazing thing that I cannot tell here. You will know at the end of the project because we have NDA, I think. So any other related work? I have to answer this question, right? Because otherwise I cannot say my project very proudly that we are the first blah blah blah. Yes, there are. We are specifically, precisely speaking, we are not the first one. Strictly speaking, many researchers in the community has tried the Wi-Fi implementation. Such as the first row is our implementation. The second row is from WARP, which is originated from Rice University a long time ago. I think some of you use that IPGA design, but it's pure IPGA. There's no Linux, no native Linux framework, right? And National Instruments, LabVIEW, they have the whole IPGA Wi-Fi application, Wi-Fi design based on USRP, right? With the X300 series where big IPGA inside. If you have budget, yes, you can use National Instruments. And also this work is also quite good. They also design IPGA Wi-Fi implementation, and they also support MIMO. But they use the PC as running the Linux. They set up the USB between the IPGA board and PC. Compared to them, I think our unique point is the SoC. Our Linux and the Wi-Fi is on the same chip. And Microsoft, long time ago, Microsoft has achieved software real-time processing of the Wi-Fi protocol. You should check that paper. That's a quite amazing result a long time ago. But one little thing I should remind you that their implementation actually cannot achieve fully real-time operation of the acknowledgement, because Wi-Fi need you make acknowledgement in 10 microseconds, right? That means when you receive packet, you need to do lots of processing and generate acknowledgement in 10 microseconds. In the Microsoft implementation, they can only generate the acknowledgement for long received packet, not for short received packet. Because if the packet incoming is too short, they don't have enough processing time to generate acknowledgement. But for long incoming packet, the Microsoft solution, yeah, they can generate the 10 microsecond reply in time. Okay, this one from GNU Radio, I guess the author, I met the author, I know the author a long time ago. Many people already use this GR802.11. This is quite good project for you do experiment over when you only need transmit or need monitor, right? If you don't need the real-time interaction with commercial chip, this is quite good starting project for the Wi-Fi research based on GNU Radio. I won't go deep. You can check the slides later, find out all the links. Only try to emphasize our unique point is that our design is based on system on chip. You have very low latency between your Wi-Fi card and computer, which is also in the same chip. So is open Wi-Fi hardware expensive? That's a very important question. We care this a lot because it matters for the community. Actually, if you don't have hardware, right, you don't have budget, you can try the open Wi-Fi in our testbed. Actually, the same testbed as the previous speaker, the iLab-T in the IMEC facility. We have installed open Wi-Fi board, several boards there. You can try it remotely. If you have budget, right, you can use this quite small software-defined radio board, system on module. I think built by analog device, Zinc IPGA and analog device front end on the same module. We have ported design on it. We will port the design to more and more boards, and recently there are quite cheap board, I would say, built by a Chinese company. It's called NH7020, that has the same IPGA as the Z board. We are working on the Z board. Currently the progress is significant, but still some issue we need to solve. I believe Z board is possible, and currently maybe Z board or 7020 is the minimum IPGA we can use for this project. Okay, last try to push you. If you are not sure should I use it or not, actually you are not obliged to use it. Just try to do some advertisement, although it's forbidden here. Yeah, I know. So, well, just like the first version of Linux, right? At the beginning, I don't think Linux target is to beat IBM Unix, beat HP Unix, right? At the beginning, it's just a mimic work of the Minix, which is used to teach students the operating system, right, in the university. That's just first mimic work of from Linus, because she is not satisfied with the Minix license condition, if I remember correctly. So he make the Linux first version by his own in his dorm and then release it. So what happens next, right, in the past many years you have seen. So we hope more and more people can just try the open Wi-Fi project, not just compare our design to the commercial Wi-Fi chip. That will help us a lot. Yeah, talk is cheap. Show me the code. Yeah, you can find our code on the GitHub. Thank you. Maybe, well, this is a normal presentation. I will ask you a question. Actually, we have observed this phenomenon a long time ago. The community in the CPU domain, right? Computer science domain. The open source activity there is quite a lot. They are quite active. RISC-V, ARM, Intel CPU, right? Linux, many open source projects, even open source firmware, right? Open source BIOS. On the other side, in the connection domain, Wi-Fi connection, cellular chip, Wi-Fi chip, Bluetooth chip, all the connection chip for the radio link. This domain is quite close. Almost all the connection silicon are black box. I don't know why, so I asked this question. Meanwhile, I try to do something in this domain to do this open source Wi-Fi chip. So, talk is cheap. Show me the code. I have to show you something. Not the real code, but I try to explain a little bit about the whole project building blocks, right? At the bottom, this is the R frontend in the black. This is AD93661. There were two RX, two TX, ADC, DAC, right? And fortunately, they have the AGC module inside frontend. So our baseband only need to read the real-time AGC gain to assist our FPGA to calculate real RSSI. That's the frontend, which is not built by us. Okay, on top of the frontend, the blue one is the FPGA building blocks. At the beginning, we thought, okay, Wi-Fi implementation, maybe we implement the OFDM transmitter, OFDM receiver, hook it with Linux, then that's it, we're done. We celebrate. Finally, we realize, no, it's way more complicated than your imagination. Way more things than just the physical layer signal processing. You see, the physical layer is over here, Open OFDM RX, Open OFDM TX. These two physical layer block, they take IQ sample or take packet, right? Then generate packet or generate IQ sample. Then huge things are out of the physical layer. This branch is for the receiver path. We have a DDC, antenna selection, feed IQ to the physical layer, then take the packet to the Linux. Meanwhile, not all the packet will go to Linux. If you check the Linux MAC 802.11 framework, they tell you what should you do in the Wi-Fi chip. You should do a packet filter. Linux, otherwise the workload of Linux is too much. Here we also need to handle all the DMA stuff, RX DMA. From IPGA to Linux, we set up ring buffer DMA, actually keep running in the background. In the driver, we check the DMA status. That's why we know what's the latest packet. In the central is all the CSMA low MAC layer in IPGA. You need lots of functionality. You can check the standards. They define everything very clearly. You need CCA, right? Detect channel is busy or not. Two methods. Based on RSSI has to be precise, right? Otherwise, you have wrong answer. Based on preamble, which is from the OFDM receiver status. Okay, you output channel status to the CSMA CA engine. In this engine, you do the random backoff, right? According to your contention window, etc., all the parameters in the standard. You also need to do the virtual carrier sensing. Virtual carrier sensing means that you monitor all the packets in the channel ongoing. In those packets, there's a field called duration. The duration tells you that transaction or that interaction will occupy the channel for how long, for how many microseconds. That's called virtual carrier sensing. To get that information, you have to pass all the packets incoming, pass the duration field. Not only, actually, you also need to pack MAC address, everything, feed to the CSMA. And packet filter also need this pass result. And you generate the ACK CTS reply in real time. Do retransmission in IPGA because Linux give you a packet. Meanwhile, Linux will tell you, for this packet, you should try this MCS for how many times. Try that MCS for how many times. IPGA, you need to do that. Linux, wait for your result. Work hard. So wait for the ACK, right? When you send the packet, your IPGA need to wait for the ACK. Otherwise, you cannot tell Linux that this transmission is successful or not. This is TX path, which do the reverse processing as the RX. Okay, above IPGA, those are driver modules. AD driver communicates with the front end directly to do the channel tuning, right? TX, RX stuff. And the TX interface driver configured this part, the DMA driver, right? The Xilinx DMA driver. We modify Xilinx DMA driver tailored for the case. And TX-RX driver, DMA driver. Basically, those drivers configure the IPGA registers, functional registers to control the behavior of your IPGA design. Above the driver, okay, that's the fortunate thing. Linux define everything. Mac 802.11 framework. Linux define a whole bunch of APIs they need. You don't need to implement them all, but you need to implement necessary subset, right? To support ad hoc mode, AP mode, station mode, or monitor mode. Different mode need different combination of those Linux APIs. Okay, basically that's the whole design of the Open Wi-Fi. Questions? Okay, please.
A simple question. So, could you please have a look at this system subsystem? Yeah, right.
Yeah.
So once you do the virtual carrier sensing, what about in the time the Linux asks you to send one thing? So where is the logic to handle it?
Okay, the question is when we do virtual carrier sensing, if the packet comes from Linux, what should we do, right?
Yeah, which logic? Which part of the logic?
Okay. For the TX path, actually there are two queues. Actually, Linux asks the chip with better has at least 4 queues, but currently we implement 2. It's still just work. So all the packet comes from Linux. They cannot go outside immediately, right? First into the queue. And CSMA engine will decide when is the right timing for next packet to go outside. Different queue could have different priority or different purpose, such as for beacon, for data, something, but there's lots of flexibility.
So that means that when you do carrier sending, probably you can send out other high priority packet, but hold on this low priority packet, right?
If the sensing module believe there's a chance for us to transmit, right? Then we can select one packet from one queue to transmit.
Thank you.
Is anyone else leaving? Okay, could you go ahead and leave? I realize this gets a little bit confusing. We scheduled tightly.
Maybe that, yeah. You. CSI information, right? Currently, you can capture the CSI in IPGA, but I think we will do that because one benefit of software-defined radio is that we can have deep access to the physical layer. Please. Please. Are you? Okay, thank you. Okay, you.
My question is about the front end. Do you plan to extend your work from design to front end? Because the front end now is the next black box. It comes from ADI.
Yes. Their front end actually is quite complicated. I believe there are firmware. There are lots of digital processing. Yeah, but this.
Follow up on that point. Have you looked at the RF SOC chip instead of the MP SOC?
RF SOC.
Yeah.
Oh, I know that latest generation with high-speed ADC DAC, right? Maybe we will try it later. Yeah.
That could help solve that problem.
One proprietary thing to a different proprietary thing.
You still have question?
I know you're obligated to say that as an ADI.
Like, what are your next priorities on this?
Next priority. Next priority, I think we still need to test the design with many commercial device compatibility issue. For instance, currently it works with laptop, iPhone, but we do identify.
We'll need the microphone.
Okay, we do know that, for instance, the OnePlus Android phone always has issue with our design. So maybe it's related to the different chip has different signal quality. We still need to debug. We try to make it more stable and compatible to as many as possible.
Thank you.
Thank you.
Thank you very much. Everyone enjoy yourself. And move away from the door when you start talking.
somehow there's this funny algorithm from the organizer of this